Hi, I'm Owen Welch, and I'm the lead researcher for this project and a high schooler from Palm Beach Gardens, Florida.
I'm Michael McCarty, and I'm a middle schooler from Palm Beach Gardens, Florida.
And I'm Aadhya Shah, and I'm a high school student from South Florida, and we're here on behalf of the Wolfpack CubeSat development team to present our experiment on lunar dust mitigation on spacecraft in a low-gravity freefall environment. To begin, we started this process of the lunar rover in 2018, and students since then have worked to make this into a reality. We have done this by employing methods of problem-based learning, which is essentially learning about concepts by solving real-world problems about them, which then allows students to apply the necessary skills for these concepts. So for this rover, students have learned about the skills necessary by playing an active role in the design and experimentation processes. Problem-based learning has shown to increase students' performance in school and shown proficiency in answering multiple choice questions by 60 to 70% based on their grade level. It has shown to give students a better understanding of their knowledge and its application instead of just knowing facts and reciting them. Students have been taking the applications of problem-based learning in stride and are attempting to solve one of the most prevalent issues in lunar travel. Since the Apollo era, there have been difficulty in operating due to lunar dust, which can be found on the moon's surface. Lunar dust is similar to soil here on Earth. However, due to countless micrometeorite impacts over time, the lunar dust has been ground into a very fine and sharp substance over time, making it have a very abrasive nature. In addition, exposure to UV and background radiation has also photoelectrically charged the lunar dust. As the radiation strikes the dust, it removes electrons, causing it to be positively charged. As Coulomb's law states, like repels like, so the lunar dust repels from itself. Because of its low mass, the force of repulsion is greater than the force of gravity, so the dust creates a cloud of its sharp substance above the lunar surface. In addition, because the dust is positively charged, it then sticks to equipment that is negatively or neutrally charged, such as astronaut spacesuit and other technological equipment. This dust then also sticks and adheres to the solar panels, decreasing their voltage and efficiency. The abrasive and adhesive nature of this dust is what makes it such a prevalent issue in lunar travel. Because of the abrasive nature, it cuts through astronauts' spacesuits and their Kevlar, and it also erodes the equipment used in lunar travel. The elements that make up the dust are also highly toxic and is composed of an element of crystalline silica, which is a known carcinogen. In addition, when inhaled, the lunar dust damages the lungs, which scientists now call lunar hay fever. This wouldn't be an issue as astronauts are wearing their spacesuits, but because of the adhesive nature of the lunar dust, when entered into the capsule and astronauts take off their helmets, they then inhale the dust, which is what creates the issue.
Now to be able to solve this lunar dust problem, we designed the Mars lunar rover. The design of the Mars lunar rover is based off the volume of a 1U CubeSat. We currently plan for the rover to land in the shape of a 1U and then expand into the footprint of a 2U CubeSat with a depth of 1/2 U. This means our dimensions will be 20 centimeters by 10 centimeters by 5 centimeters, and this will be done with the use of nitinol wires. Now for the locomotion of Mars, it has gone through many renditions, with the most prominent being a flexible wire mesh tire displayed above. So these tires allow for a lot of flexibility on the lunar surface, meaning the rover can traverse the rocky terrain more easily. As for the EPS, solar panels will be the main component of the EPS of a Mars, and we currently plan, after extensive research, we've found an 8.2 volt battery weighing in at 86 grams. Now to be able to properly communicate with the Mars, we hope to launch with the Astrobotic Peregrine lander. If we are to launch with Astrobotic, a Mars would send its data to the lander, which would then be transmitted to Earth. So based on the quality of images a Mars takes, it will determine the accuracy of navigation and location. This being said, we've yet to find an accurate camera given our cost, size, and energy constraints. Now to be able to have an accurate experiment, it was necessary to create an accurate simulation of the lunar environment. To do this, we designed a box that simulated the vacuum on the moon. The box was built with 6 Lexan plastic sheets held together by an adhesive sealant. On the top of the box, there's a gate valve attached to a rubber gasket, which allows for the creation of a vacuum. Inside the box, indium tin oxide or ITO plates, a DC power supply, purchased UCF lunar regolith, and solar panels will all be used for the experiment. So when we first began testing, we had to determine whether or not the ITO plates were a viable material when attached to the solar panels. To do this, we tested the voltage output of the solar panels with and without the ITO plates on top of them. It was concluded that the ITO plates only resulted in a 2% decrease in voltage. From there, we tested the electric fields of the ITO plates on the lunar dust simulant. However, we found there was no effect. Then from further research, we realized that our lunar dust simulant was not ionized like it is on the lunar surface. So our first method of doing this was through tribocharging. Tribocharging, otherwise known as point contact charging, is the effect of having two different materials make contact with each other and then separate. This usually results in the transfer of electric charge. So to do this, we poured the simulant over high quality ABS plastic blocks, and then we shook the two materials together in a plastic box, hoping that the simulant would then transfer an electron to the plastic blocks, leaving them positively charged. But unfortunately, there was no noticeable difference in the simulant's charge after this process.
From there, our next step was to reach out to our contact at UCF, who we purchased the lunar regolith from, Dr. Metzger, who recommended that we use a Van de Graaff generator to create a long-lasting ionization of our lunar dust simulant. For our criteria of ionization, we were not looking for levitation, perhaps because of the greater gravity here on Earth compared to that of the Moon. We were simply looking for repulsion. And in order to see this, the force of electric repulsion had to be greater than that of the gravitational pull of the Earth for particles greater than 10 micrometers, or this repulsion force had to be greater than the van der Waals adhesion force for particles smaller than 10 micrometers. When using the Van de Graaff generator, we did find that there was consistent ionization of the particles as they repelled from themselves for a long period of time. In this case, we only saw it for a minute, but this depends on how long we run the generator for and how close that the particles are to the generator in our process. From there, once we had ionized the dust particles, we tested the ionized dust with the ITO plates, or the electric field, by placing the ITO plates inside of the container, distributing lunar dust simulant on top of the ITO plates, and exposing them to the Van de Graaff generator. After this, we hooked up the DC power generator to the ITO plates and began to run preliminary tests by passing voltage through to the ITO plates. We, in preliminary tests, saw results and saw that the dust began to repel from the ITO plates. However, we did not test long enough or have the correct equipment to find accurate, conclusive results. So we're still in the testing phase, and we're still trying to find the correct materials to create accurate results that we can then apply to our lunar rover. In future experiments, we are obviously going to repeat experimentation and find better materials to get more accurate and precise results. And we're also going to revise our methods to create a better system. We also want to retest the environment, as we are currently using commercial off-the-shelf parts, as you saw in the picture earlier from the materials and methods slides. So we're going to try and create a better lunar environment that we can more accurately test our experiment in. Hopefully trying to find a university or someone to give us these materials. The next steps of AMARIS are to complete more tests and find a more refined version of dust mitigation, and we're set to construct the rover itself following experimentation in 2022. We need to find the materials necessary to construct the rover and then apply either the ITO plate system or the best system that we find to the lunar rover. From there, we're going to build, test, design, and soon enough, launch our AMARIS rover to the moon. Thank you, and if you have any questions, we're here to answer them.
Are there any questions from the audience? Yes.
Congratulations for this presentation. I have a question about the ITO plates. On the last slide, it was mentioned that apply the plate system to the rover. Could you explain where it should be implemented and what is the function of these plates?
So yes, on this specific slide of our idea for our rover, we'll be putting the ITO plates on top of the solar panels because they are clear and this will be their best application. I'm not sure if we don't actually have any pictures of the plates, but they are simply just a small clear conductor that we would place on top of them to repel the lunar dust and hopefully increase the efficiency of our solar panels by decreasing the amount of dust that collects on them.
Okay, anyone else?
Yes.
Yeah.
Excellent presentation. Very impressed. And congratulations.
Thank you.
Curious to hear your thoughts on if it would be feasible and possible to effective design surface infrastructure on the surface of the Moon and Mars to generate these electromagnetic fields to mitigate dust plumes and dust storms.
Right, so that would be a little bit tougher with this design because that is such a large scale event. So I believe it's possible with electric mitigation, but I think the more likely plan of action with such large scale events would probably be structures that could withstand such storms. Like one of the leading ideas right now is to create structures using the lunar dust itself, melting it down and creating a solid wall or solid object that could then withstand the effects of the lunar regolith. But I think it could be possible to apply this on a larger scale. I just have to see the future where it takes us. So.
Okay, then let's think again our speakers team.